Okay, so in this next section, we want to look at another type of system. So now we have a lift and it has two particles inside it, and we're really concerned with the internal forces. So the forces in between the red and the yellow particles. For us to really get an understanding of this, I want you to start by thinking of a comparison between the particles while they're inside the system and while they're outside of the system. So what I mean is, what would the motion of the particle be if it was in free fall compared to if it's a part of the system? So this red block, if it was falling freely and it wasn't contained within the system, it would actually fall a lot faster than it currently is. The reason that it doesn't is because there's a force from the yellow block. There's a force from the yellow block being applied to it, and that force is actually slowing it down from falling as fast as it would if it was in free fall. So let's model that. So we'll start by considering the red block, and only the red block, which has its own weight. And as I said, there's a resistive force, which we'll just call R, which is slowing it down from moving as fast as we want it to move. When we move over to consider the yellow block, we do need to think about Newton's third law, which says that every action has an equal and opposite reaction. Well, the force that the yellow block was applying to the red block, the force that was slowing it down, is actually going to be exactly the same as the force that the red block applies to the yellow block, a force that is effectively speeding it up. So, once we've found this unknown force on the red block, we can actually model it on the yellow block as well, going in the opposite direction. So it's just useful for you to be able to interchange between these forces using Newton's third law. So that the force going into one is the same magnitude as the force going into the other, but the opposite direction. So when it comes to modeling the forces on the yellow block, we can start with that reaction force. We know that it's going in the opposite direction, but if we found its value, we can use it. The yellow block also has its own weight, which we can model, and there's another force that is slowing it down, the force from the floor of the lift. So here are the three forces we would model on the yellow block. Okay, so this was all without numbers. So let's actually try an example with some values involved. So here in this question, we've been told that a light scale pan is attached to a vertical lighting extensible string. This works exactly like a lift does. And we've been told that inside this pan, there are two masses, A and B, 400 grams and 600 grams. So I'm instantly going to write these in terms of kilograms and one on top of the other. We're also told that the scale pan is rising or is raised vertically and its acceleration is 0.5. So just thinking about the whole system here, we're going to resolve some forces. I've got the tension moving in the positive direction, and I've got the weight of these two objects moving downwards. The pan itself has no weight. We are told it's a light scale pan. So the weight of these two objects together is 1 kilogram, which I'll represent as 1g. So using F equals ma, we get T minus 1g equals 0.5, which I can rearrange to find a tension of 10.3. In the next part of the question, we were asked to find the force exerted on B by A. And as I've described before, the force on B by A is the same as the force on A by B. So we can go ahead and just model particle A and all of the forces acting on it. All right, so just a quick diagram. A has its own weight, 0.4 g, and this resistive force, that's going to be the answer to the question. It's the force on B from A, and it's the force on A from B. Okay, it's a force that is helping A in moving upwards. It's working against gravity. It's working against the weight of A, which would want it to move downwards. So let's go ahead and plug this into F equals ma, rearrange to get an expression for R, and we see that R equals 4.12 newtons. So particle B is applying 4.12 newtons to particle A. And as we said before, that means that A is applying 4.12 newtons to particle B. What force is being applied to B from the light scale pan? Once again, that's going to be an upwards force, resisting or working against the weight of the particle itself. So let's go ahead and resolve. H is positive, R and the weight are negative. We know a value for R, so we can just substitute that in and rearrange to find out what H is. Really, these two diagrams are going to occur each time. We consider A first because it has fewer forces, and then we can move on and consider B because we'll then have less unknowns since we already found the reaction force in between A and B. So the force exerted on B by the scale pan is the same as the force exerted on the scale pan by B, and that is 10.3.